everyone. Welcome back to the lectures on Introduction to Multi-Agent Systems. In today's lecture, we'll derive the solution of the Laplacian flows for the case of undirected networks. We'll also look at the conditions which can guarantee consensus for the Laplacian flows. Remember that the Laplacian flow that we're looking at is built on to model the behavior of a set of agents who are all interacting with each other. So the question that arises is, does this interaction somehow play a role in determining whether or not the agents achieve consensus, which is something we will answer in today's lecture. So let's get started. Start by writing out what the Laplacian flow looks like. This is something that we have already seen numerous times. For an undirected graph G, and corresponding Laplacian matrix L Laplacian flow is given by x dot equals minus Lx. What does this graph represent? This graph represents a set of n nodes which are connected to each other via edges. So we know that the graph here, G, is in fact, it consists of a vertex set V and a set of edges E. So these n nodes sitting in the graph, or n vertices, simply denote, for a practical system, n agents. What are these n agents doing? The n agents are communicating with each other using the Laplacian flow. Something that we have already seen before is that when we are using the Laplacian flow, then the ith agent state xi evolves as this. The derivative xi dot of t is simply equal to aij times xj minus xi, where j is the set of neighbors of I. So now we have the set of n nodes, or n agents, whose dynamics is given as this. So the question that we are now trying to answer, that is our objective, is to see under what conditions do they achieve consensus. So our objective is to determine the conditions under which agents achieve consensus. So how would we go about answering this? The starting point would be, when we say the agents achieve consensus, we mean that ultimately all of their states x1 to xn become same. Not only do they become same, they also remain the same thereafter, meaning consensus must be a steady state behavior of the system, such that the derivatives of the states, time derivatives, do not change at all. So we are interested, obviously, in analyzing the steady state behavior, which we want to be equal to the consensus state. So let us observe what happens at steady state. So at steady state, we have x dot being equal to minus Lx, and we say that this should now be equal to the zero vector, meaning none of the states now change. Notice that when can an x, when applied to the linear transformation L, so we can always view the Laplacian, it's a square matrix, we can view it as a linear transformation. So now, in that case, we say that any x for which L times x is equal to 0, all of those x now lie in the null space of the matrix L. So this implies x belongs to the null space of L. So here, this is defined as null space of. So what do we ideally want? We want the system, first of all, to achieve steady state, meaning we want the x of t to converge to some value x bar such that few things must hold. What are those few things? The first thing is L times x bar, first of all, should be equal to the zero vector. Second, not only that, we must also achieve consensus, meaning x bar 1 equals x bar 2 up to xn bar, where please remember that x bar was a vector or is a vector whose entries are x1 bar up to xn bar. Okay, so this is our desired behavior. First of all, the state should move towards x bar, and then the x bar must be a consensus state. So now the question is the consensus state, or does the consensus state lie in the null space of the Laplacian? We know it does lie. Why? Because of the properties of the Laplacian. And we have studied it several times, so I'll just write, we already know that L1n equals 0n. What does this imply? This implies that span of 1n belongs to the null space of L. Then our job is done. But the question is our job really done? Not really. All that it says is, so span of 1n implies the consensus state because every entry of the vector, when it is equal to this, all of the entries are the same. Hence, consensus has been achieved. However, it is not sufficient to say that span of 1n belongs to the null space. The reason being that the null space might contain entries which do not lie in the span of 1n as well. So when does that happen? So let's ask the question. Does every vector in the null space of L imply consensus? In other words, for does every x bar belonging to the null space also satisfy x bar belongs to span upon n? Let's try to answer this with an example. So this is now a question. Let us take any digraph, any undirected graph. Let's take a very simple graph like this. Suppose this is how they are connected. And let's number the nodes as 1, 2, and 3, 4, and 5. So what does the Laplacian of this matrix become? Laplacian is simply given as and 2 has 2 nodes connected to 1 and 3, and node number 3 is connected to node number 2 only. Similarly, node number 4 is connected only to node number 1 and node number 5, and node number 5 is connected to node number 4. So this is now a Laplacian. Let's calculate a vector, all the vectors in its null space. What do they look like? Do they only contain the consensus vector? So this gives us a set of linear equations. Let me write up all of them. Minus x1 plus twice of x2 minus x3 equals 0, minus x2 plus x3 equals 0, and x4 minus x5 equals 0, and the last one is simply minus x4 plus x5 equals 0. If we solve them, we simply get x1 equals x2 equals x3. And if we solve the last two, we simply get x4 equals x5. So any vector which satisfies both the conditions, C1 and C2, belongs to the null space. Let me give you an example of a vector. Let's take the Laplacian first. Now let us consider a very specific vector. Okay. Let me write the value of the vector here. That is 1, 1, 1, 2, and 2. So notice here that x1 up to x3 are the same as specified here, and x4 and x5 are also same. However, so first of all, does it lie in the null space? Yes, you can see that all of these entries evaluate to 0. Hence, the vector shown here does lie in the null space. However, does not belong to the span upon n, meaning is not the consensus state. Meaning, from this example, we know that the null space of the Laplacian L, denoted as n of L, can contain vectors other than the consensus vector. The consensus vector is any vector in the span of 1n. So if we ensure, so can we say that at steady state consensus is guaranteed? No, it is not always guaranteed, because sometimes we can converge to a vector which does not indicate consensus. Meaning, in order to make sure that consensus is guaranteed, we have to make sure that the dimension of the null space, first of all, is equal to 1, and it contains the vectors which lie in the span of 1n. So obviously, this implies that for consensus to occur, we have to ensure that the dimension of the null space is equal to 1. Secondly, the null space is equal to the span of 1n. These are the two conditions which are required for consensus to occur. So obviously, now we know the answer to our question. In order to achieve consensus, we are looking for undirected graphs such that when we construct the Laplacian, the null space of that Laplacian has a dimension equal to 1 and contains vectors which lie in the span of 1n. So now we simply need to construct such undirected graphs. So I would ask the students to pause the video here and see if they already know the answer to this. Again, this is something that we have discussed several times in the past. So what is the answer to this question? So now we state the conditions for consensus. Before that, let's summarize the properties of the undirected graphs that we already know. Consider an undirected graph G and its Laplacian matrix L. Then the following spectral properties hold. Spectral properties hold for L. What are those properties? The first one is something that we saw in the previous lecture. Lambda I belongs to R for every I belonging to 1 to n. Meaning, all of the eigenvalues are now real valued. Second, if G is connected, then lambda 2 is strictly greater than 0. So, okay, we must first define what is lambda 2. So, before this, we write, we can then arrange the spectrum as in this increasing order. Now we can say that if G is connected, then lambda 2 is strictly greater than 0. Note that lambda 2 is the second smallest eigenvector. If the second smallest eigenvector is greater than 0, obviously every other eigenvalue following it, lambda 3 to lambda n, are also, each one of them is greater than 0 again. Meaning now there is only one entry, one eigenvalue, which can take the value equal to 0. So obviously we know that lambda 1, so this is trivial, something we have discussed numerous times. We know that 0 is an eigenvalue of the Laplacian. So the smallest eigenvalue is obviously equal to 0. Okay. Now let's write up a few properties about its eigenvectors. So we already know that the eigenvectors for distinct eigenvalues are mutually orthogonal. Additionally, so if I have an eigenvector vi which satisfies av equals lambda I vi, then it also satisfies vi transpose A equals lambda I times vi transpose. Meaning vi can be treated as both the left and the right eigenvector because of the symmetry of L. With this, we are now ready to state the solution and the conditions for consensus. We define a term yi of t, which is equal to vi transpose this implies the time derivative of yi of t is equal to d by dt of vi transpose x of t. We can take vi outside and we have d by dt of x of t. Now, since we are following the Laplacian flow, d by dt of x of t is nothing but minus Lx. So let us substitute it here. Minus Lx. The minus can come here and we have vi transpose L times x of t. Remember that vi is an eigenvector of L, hence this becomes lambda I times vi transpose times x of t. Again, vi transpose x of t is yi of t. So what do we end up with? We end up with d by dt of yi of t being equal to minus lambda I times yi of t. So what have we done in this process? We defined some state yi of t, and we see that if we use this particular formulation, then all of the states yi of t are getting decoupled. That's an important observation here. All the states yi's have now become decoupled. not only that, we can in fact solve these to get the solution. yi of t is equal to e raised to the power minus lambda it times yi0. So effectively, we have n differential equations associated or arising out of the state x of t, and for a symmetric matrix, all of the VIs are actually orthogonal to each other and can always be selected such that they are also orthonormal. Again, this is something we discussed in the previous lecture. Because of this, we can now write the solution x of t in the following manner. Sorry. The solution of the Laplacian flow is given as x of t being equal to y1 of t times v1 plus y2 of t times v2 and yn of t times vn. So we get this from the spectral decomposition theorem. We can also get the same from there. So now we can substitute the values of values of yi's. We get x of t is equal to e raised to the power lambda minus lambda 1t times v1 transpose x0 multiplied by v1. The second term is equal to e raised to the power minus lambda 2t v2t times x0 times v2. And similarly, the nth term is given as e raised to the power minus lambda nt vn transpose x0 times vn. So what eventually happens to each of these terms? Let's see it now. Let's look at the first term. So remember that in the case of the Laplacian, we have lambda 1 as being equal to 0, and to ensure orthonormality, we can choose v1 as being equal to 1 by root n times the vector 1n. For orthonormality, we use these. Hence, the first term evaluates to, let's see, lambda 1, this term becomes equal to 1. So we are left with v1 transpose x0 times v1 again. So what is v1 transpose? It is, I can bring root n outside here and write all ones times 1, 0, which is the initial condition vector. And this is again multiplied by, I can bring root n here, and this is multiplied by vector of all ones. We have 1 by root n here, we have 1 by root n here. So together, I can combine it to write 1 by n. When this term gets multiplied with this, we simply get a summation of all of the initial conditions, and then that summation is divided by n, which gives us the average of all the initial conditions. So again, this is equal to, the first term is equal to the average, let's simply write AVG, of all the initial conditions multiplied by the 1n vector, meaning if I write it further, this is equal to average is a scalar and that gets multiplied to every entry of 1n, meaning all of the entries of 1n are the same and are equal to the average value of the initial conditions. So as we can see, all the entries at steady state of the agents become equal to or become equal. And the value that they become equal to is the average of the initial conditions. However, note that there are some other terms as well which are contributing to the state. So what happens to all of the other terms? If the undirected graph is connected, then we know that lambda 2 onwards, every other eigenvalue is greater than 0, meaning with time, all of these terms simply decay to 0, every other term. And this is the term which gives us consensus. So while all of the other terms converge to 0, xt asymptotically or rather exponentially approaches the consensus state given by the first term in the solution here. Let's write it again. To summarize, all the other terms given by e raised to the power minus lambda I t vi transpose x0 times vi decay to 0 or tend to 0 as at steady state. Implies x of t approaches the first term, which is given as the average of the initial conditions multiplied by the 1n vector. Implies the agents achieve consensus. Not only this, right, a very interesting observation that consensus is contributed by the eigenpair lambda 1 and v1, whereas disagreement is contributed by every other eigenpair lambda I, vi, where I belongs to 2 to n. And this is what happens when the underlying graph is actually connected. So now we know under what scenarios we can always achieve consensus. With this, we'll end today's lecture. In the next lecture, we'll look at the properties required for consensus in the case of directed networks. Thank you.